let's get to the business. What is it? When we talk about image quality, first and foremost, we want to talk about what do we mean by noise and scattering. Okay, scattering, because it was a named one, you might easily quickly spot it, right? Compton scattering. So we will come to scattering after we completely deal with the noise, right? Scattering will be towards the end of this module. So noise, what is noise? What we have pretended so far is, oh, I have this physics, the X-ray tube generates photon, it comes through, through light, you do the filtering, restriction, it goes through the body, interacts with photon for photoelectric effect. Compton scattering, we said scattering will delay the discussion after completing the noise part. So essentially you had the signal part, right, the photoelectric effect, and then we said that signal goes, hits, you have your intensifying screen, collimator, goes, hits the film. So essentially we have pretended whatever falls on the detector, right, is truly faithfully reproduced at the output optical density which the doctor is interpreting. But in reality, what do you think? Oh, in reality that's not as simple, because you are measuring this, all this is fine, but then when you do the measurements, there could be fluctuations, there could be randomness, right, which will contribute to the source. In our case, we need to identify what is that source, where that fluctuation could come from. Okay. So now is the time to recall where could it come from the physics of it. Just think about from the start of this process of imaging. Physics, right? Okay, I have photons that are coming out. So essentially what we have talked about is X-ray photons, n number of photons are going through, it is getting attenuated, reduced number of photons are coming out, that falls on the detector, right. But how is this photons generated? Photons are packets of energy, electromagnetic photons or electromagnetic X-ray is what we are talking about, right, interaction with the material. Oh, those are essentially packets of energy, right. So is that all nice and clean, or could there be randomness? Oh, in fact we did talk about the time arrival, right, when you generate this X-ray burst, the n that comes out, right, it has a statistical property, right. What is it modeled as? The time arrival onto the detector. We showed one of the random variables. What was that? Poisson. So now we can essentially say detector does not faithfully reproduce the incident intensity. Why is that? Because you have randomness. Where is that randomness? The X-rays arrive in discrete packets of energy. Okay, it's a random event, it's a burst of X-rays. So given that, I could have the same material, but adjacent locations may experience different n number of photons, because the burst creates a population of energy of that photons, and each one arrives at different time instance. So therefore, even though it is the same material adjacent locations, right, you may get different n, slightly plus or minus the neighbor. So there is a fluctuation around, right. So that fluctuation, we also used the term called quantum motile, right, this fluctuation. So because of that, what you have is this fluctuation is your noise. So what we will do is we will take, now the question is we will have to define this little more carefully. So we understand where the source of noise is. Now we need to model that. It's not going to be new. We have an idea on this randomness, so you know where we are going. So let's take a condition right here. So you had this simplicity, we have taken a profile. For example, we had a square object, right? Remember the prism slab. So leave alone other stuff, right? When you have the detector, it comes out. So on the detector, you have a square cross section, right? If I have a rectangle, I have a rectangle cross section. So this is my object, right? This is my object, my palm alone, right? This is my object, right? I am keeping it like this. This is my object. One side is X-ray coming, other side is the detector. I am keeping this detector, this object on the detector to avoid magnification, all those blah blah blah. So that means my shadow is going to be like this, right? This is the region on the detector that is going to be hit. So if I take a profile, if I take one line of this, right? No value, no value, no value, high value, high value, no value, low value, low value, right? So this is your, ideally this solid line is what you would have had, but given the randomness, you are essentially going to have, what is going to be picked up is going to be having fluctuation, right? So now the question is, fine, we see this, how do we now study this further and talk about the image quality? How do we define the image quality for this based on the measurements? Same definition, fluctuation is your noise, meaning your standard deviation, variance, right? What is your signal? That is, so signal is defined in the context. In our context here, for example, what is our signal? Oh, we want to see how tall this target is standing out compared to the background. I want to spot this target in the background. I want to identify this structure, right? I want to identify this target from the background, tease out this target from the background. So that means my signal is how well I can see the target from the background. So my signal in this case I am defining as the difference between IT and IB. So this is where I want you to be careful, okay. So we are going to talk about, always when you talk about noise, noise itself is not, I mean, you need to know what the noise is, but it is always in the context of signal that we are worried about the noise. So it is always the signal to noise ratio that will be analyzed. So when we talk about signal to noise ratio, it is very important you read the material to see how they define signal and what is the source of noise. This, even though everywhere they will use signal to noise ratio, contrast to noise ratio, contrast, you have so many metrics, and the definition for signal to noise ratio could be different. So last time when we used the signal to noise ratio, we just talked about mean to standard deviation, which is a very standard way of doing it. Whereas here, if you notice, our signal, we are defining it as actually how much can the target be seen compared to the background. So our signal, we are defining it as difference between your target and background, right? So you are defining your signal in terms of local contrast. So local contrast is IT minus IB by IB. So your signal is defined in this terms, okay. So now the question is, fine, what is my noise? Noise is just a fluctuation in the background, right? Fluctuation in the background, or the standard deviation, square root of variance, right? So random fluctuations in the number of photons arriving in each small area of the detector, that leads to noise, right? So what is that? Do you have a model for that? Yes, we do, right? We do. Remember this random fluctuation. So if you know the characteristics of this random fluctuation, how do we know that? Oh, we know the probability, right? Distribution function. You saw the probability density function. What was this? We know that it was Poisson. What is the characteristic of Poisson? Oh, your mean and variance are same, correct? So you can write your signal to noise ratio as IT minus IB by sigma B. So IT minus IB kind of captures your local contrast. Of course, it is normalized by IB here, the local contrast, but your signal is, we want to capture this difference. So your signal is IT minus IB, your noise is sigma of B, whatever is the background fluctuation. So I know IT minus IB, this is a local contrast that we had defined. So we could write your signal in terms of the local contrast, C times IB by sigma B. So this is your signal to noise ratio. Fine. So this is my signal to noise ratio, but how do I work this further? So I need to bring in my signal and noise more explicitly, because my noise comes from and the signal comes from your number of photons, right. So how do I expand this? We are just going to say we have population of statistics, right, number of photons that are arriving. So your signal will be mean, and your mean of the number of photons, standard deviation will be your, variance will be your same as your mean, right, because of the statistics. So I know, which is my n h mu by A delta t, this is the definition. Of course, be careful why we talk about I is equal to n h mu by, this is the regular formula, but then where does the fluctuations come? The fluctuations come here in n, right. So the number of photons, the fluctuation in the number of photons, the statistics of this gets to your intensity fluctuation as well. So your I, so your n is, in the background you are going to have nb h mu by A delta t, your sigma square is going to be nb, right, your variance is same. So if you recall your standard deviation, right, so now we can substitute this. We did similar thing before, right, but that was just signal to noise ratio, mean to standard deviation. So mean was, so standard deviation was square root of variance, and we said Poisson distribution, your mean and variance are same, and therefore we got the square root of n in our generic introduction for image quality, right. So here we are customizing it, right, with putting the NB, and you have this h mu square by A delta t. So you can get the similar thing, SNR, if you substitute as C square root of NB, nothing. So the C was not there before when we did our intro, because we defined our signal to be just mean, whereas here we have defined the signal to be local contrast, and therefore your signal to noise ratio captures C here, and then square root of NB, right, clear, straightforward. So the idea is, this is nothing new. The way we have defined our signal in this context is capturing the local contrast, and therefore your signal to noise ratio is in terms of contrast C and square root of NB. So this is where I think you need to be careful when you read, interpret some measures. You need to first make sure, means okay, first you have to make sure that your understanding of signal to noise ratio, the definition is same as what you are going to use. So several literature we define contrast to noise ratio, which is not really captured in this modules. Here we are talking about signal to noise ratio, the signal is capturing the local contrast. There are some other measures, just the contrast ratios, signal to noise ratio, contrast to noise ratio, contrast ratio. So there are several ways people try to capture it. So you have to understand the definitions, right, how they define and what they capture. The term may be same, SNR, but here notice the signal is defined as capturing the local contrast, okay. So how do I increase my signal to noise ratio? Well, proportional, right. So I can increase the contrast, or I can increase my NB, or both. Beautiful. So what contributes to contrast? Well, we talked about inherent contrast, right. We have to be able to, this is all inherent, we need to be able to capture the contrast that is there already. So, for example, in our case, if you look at the plot that we showed, we had bone, soft muscle, right, sorry, muscle and fat, right, soft tissue that was exponentially decaying, and we noticed, so x axis had energy level, y axis had the attenuation coefficient, right, relative attenuation coefficient. And so we noticed that that is the inherent contrast. The attenuation property of your bone is different at different energy levels, but that is more different from your muscle behavior, which is different from your fat behavior. So, contrast, when you talk about for any given energy level, you are talking about the difference in their attenuation property. So, this is inherent, intrinsic. So, how do I increase my intrinsic contrast? Oh, you have a choice, right? You can take the energy. So, if you recall that plot, you had lower energy, you had very good intrinsic separation. As you increase the energy, the intrinsic separation or the intrinsic contrast came down or started diminishing. So, if how do you increase the C? Oh, maybe I can use lower energy, right? If I use lower energy, I have inherent contrast over a larger range. But then what is going to happen? What is going to happen? Well, if that is the case, we notice that the X-ray energy will probably get absorbed. The intrinsic contrast is there, but then we are interested in the contrast coming out to the instrumentation, to the display image, right. So, if it is low energy, we know that it gets absorbed, and you do not really get, the number of photons will reduce. So, if I try to use low energy to increase C, my NB will go down, number of photons that are coming out will go down, because there will be lot more attenuation, it will be attenuated fully, it will not come out, lot more interaction, right. So, I mean, nothing is straightforward, that is the fulcrum. I mean, you need to understand that nothing is a one-way street. This is the challenge that you will face. We talked about, oh, I understand the image quality, I can characterize the signal to noise ratio, now I know the physics, I know the instrumentation. So, I will say, oh, increase the SNR, I increase the C, but how do you increase the C? I know how to increase the C, I will increase the, decrease the energy. But then if you decrease the energy, not your C is better, your intrinsic contrast is better, but your N is going down. So, you have to be carefully orchestrating that. Oh, one way that we already saw which is beneficial is put contrast agent. Okay. So, there is this added effort of putting a contrast agent, tailor making it, but that helped us, right. So, you can increase the contrast by putting contrast agent. So, that was so you can manipulate the contrast. So, otherwise what is going to happen? Okay, I can increase NB. How do I increase NB? Oh, the problem is if I increase NB, so maybe I can take a particular energy level, whatever contrast is acceptable, right, which I can tease out, but then produce more photons. Well, that could help, but the problem that is not just image quality, biosafety. That means we increase that exposure and number of photons, then there is a problem with radiation dosimetry, right. We talked about radiation dosimetry. So, nothing is free. So, you will have to play with this. So, what we will do is, this is an important fundamental trade-off, because you cannot get both, as for the reasons that we discussed. So, either you can improve the contrast or number of photons. In limited case, depending on how it is, for example, you can have a contrast agent and use little more photons, you can get, so you can play with this, okay. So, increasing contrast like we talked about depends on the energy level you can change, or using contrast, that is one way of doing it. Increasing the photon, again X-ray tube, you can start from the X-ray tube, right. So, filament current, duration of the pulse, energy of the X-ray, or large element. What do we mean by large element? That means I will compromise the resolution. My detector, if I have smaller detector, then I am able to localize a location, right? So then I can say this is the location, the line through which it passed and came, this is my pixel size. But if I increase the detector size, I will catch more photons because the area is increased. But what is going to happen if I increase it, then I won't be able to localize, my resolution is poorer. I will know if my pixel is 1 mm cross 1 mm, I know I will say that this came along a 1 mm cross 1 mm line of sight in front. Whereas if I make the pixel 5 mm cross 5 mm, yes, I will catch more photons, but then I will have to say this came from 5 mm cross 5 mm region in front, so I have lost the resolution. So there is always this trade-offs, but given all that, that is fine, all the inherent trade-offs are there. It also depends on more efficient detector. So we did talk about film screen, we talked about film characteristic, right? But still maybe this is something that we need to explain little bit further. So everything else set apart, how do I understand or use a more efficient detector? If I can use a more efficient detector, I definitely can get better signal to noise ratio for all other compromises as is, right? So we need to work on how do I characterize, how do I talk about the performance of, what do I mean by detector efficiency, how do I improve the detector efficiency, right? So the idea is we can put our signal to noise ratio is contrast, we identify the noise, right, the number of photons NB, square root of NB, right, the number of photons is can be done by any of these factors. So we are just, instead of writing it as NB, we have written it in terms of all the factors that contribute to NB, right. So your 5 is your number of photons per Roentgen per centimeter square, A is your unit area, right, R is the exposure, body's rad, T is your fraction of here, right, T is the fraction of photon transmitted through the body. Most importantly, your detector efficiency. So all of these contribute to increasing N. So you can play with all of this to increase the N. So what we will consider is all the other things we already talked about. It all has its effect on increasing the X-ray tube current or radiation dose, all that we already talked about. So can we just talk about little bit more on this eta, that is your detector efficiency. If I can increase the detector efficiency, I can increase my signal to noise ratio for all other system parameter settings being same. So we need to understand what is this detector efficiency. So in order to talk about detector efficiency, we first have to talk about quantum efficiency. What is quantum efficiency? Well, what is the whole process? The process is I have a photon, right? X-ray photon is coming in. In the detector, what is going to happen? This X-ray photon has to be converted to light photon, right? We are interested in this with the intensifying screen. That's the paradigm that we are talking about. So this light X-ray photon has to be converted to light photon. So what is the chance that this will get absorbed, interact with the material, right? What is the chance that if I send one photon, that photon is going to get interacted, right, get absorbed, take part with this material and create a light photon? What is that probability? So if it is just going through, coming out without interaction, you are not going to get anything, right? So this quantum efficiency is, in some sense, it is going to characterize the ability of the detector to interact with a photon and converting that to a light photon. So quantum efficiency is the probability that a single photon incident upon the detector will be detected, meaning will be detected as in it is going to interact with the material, right? And so it's a basic property of X-ray, any X-ray detector. So now the question is, okay, when you say probability, we can have this number, right? So I can have some number for efficiency, 30%, 40%, 20%, whatever you can think of. Does it really say that if I have QE, right? If I have a better QE, numerically if I have a larger QE, does it mean that that is the that is the best, or that is the detector that we want to use, right? So better QE does not necessarily mean better images. What we want is the quality of the images to be good. What this is saying is, quantum efficiency is just detecting the probability of this interaction, but not necessarily that if you have a good QE, it will translate to better images. In other words, if I give you two detectors having the same quantum efficiency, right, but you know that one of them, it has the same quantum efficiency, but one produces, right, the conversion and localization of the photons with less randomness than the other, then intuitively you will say, look, I want to go for the first one, right, because it has less fluctuations. So its ability to convert, this probability might be true, but there is a randomness, right, when you do the multiple measurements, the fluctuation, that could be a problem. So therefore we will not, without telling any further, even though the QEs could be same, if this is the description, then I would rather go for the material or the vendor with the QE might be same, but then the one that has less fluctuations, correct. What you see in the image is the noise is because of this fluctuation. So I would rather, so you can say that the QE does not necessarily translate to better images. What that does is, it just simply counts the number of photons, okay. So if there is a fluctuation in the number of photons, you will see the fluctuation. So that is what we mean. So that means this is okay, but not really, this is important, but does not really fully capture. So I need some way to say that introducing this detector is not spoiling any further, right, or in other words, I have some intrinsic signal to noise ratio because of the physics and other things that is coming in. Now I have a output image, and that output image has a signal to noise ratio. You want the detector, right, to efficiently transfer the input signal to noise ratio to the output. So the output signal to noise ratio should be as close as possible to your input signal to noise ratio. So your detector should not spoil that, right. So detective quantitative efficiency, right, quantum efficiency is your this performance characterization of how much of the signal to noise ratio in the input, intrinsic signal to noise ratio, is preserved in the output. So represents one way to characterize the performance of a detector that has direct relation to the SNR of the image it is produced, right. So what we really want to characterize the performance is of this detector is it able to transform the signal to noise ratio that is inherently there, how much of it is it able to capture. So DQE is SNR out by SNR in, square of that. So typical values you can get like this, DQE is less than equal to QE is less than equal to 1. Okay. So what do we what can we tell from this? Well, we can see that we already talked about quantum efficiency. Quantum efficiency is also less than 1, but your DQE is even less than QE. Why? Oh, in some sense we talked about having same QE, if it's not able to localize, if there is a fluctuation, then we talked about the image quality will be different, right? It will be lower. So, your QE is the upper limit, meaning 1 is the best case. Usually your QE is less than 1. Your DQE is a further degradation, right? So, that is going to be less than your QE. Okay. So, now let us take an example, right? Consider a hypothetical detector having a quantum efficiency of 0.5 and the ability to perfectly localize every photon. What is the DQE of this detector? Okay, what is the DQE of the detector? So, what is DQE? Well, DQE is intrinsic signal to noise ratio, right, to signal to noise ratio at the output, right, square of that. So, what do we have here? QE is 0.5, that is given, but more importantly, look at this. What does QE represent? It represents the ability of the detector to stop photon, right. So, that is one thing. And then what did we say? Oh, the ability to stop alone is not sufficient. You could have two detectors with the same QE, but it may have some randomness, right? It may not. But here what is it saying? QE is 0.5 and it has the ability to perfectly localize every every photon. So, what does it mean? That means I do not have any more degradation, right? I do not have any more degradation in the performance. So, how do we talk about that? Well, what we know is, what is your signal to noise ratio intrinsic, right? SNR. What is intrinsic? Oh, we talked about this, right? Number of photons, signal to noise ratio, if just signal being the mean of the signal, variance, if it is a Poisson, right, we talked about. So, that is what we are talking about here, right. So, you have intrinsic is your square root of n. So, we are not talking about contrast here, do not get confused. We are just talking about one photon, one location, right. So, we are just talking about signal and the variation around the signal. So, signal is your mean, variation is fluctuation around the mean. So, your noise is your standard deviation or square root of sigma, right, square root of your variance. So, signal to noise ratio is your square root of n, this is your intrinsic. So, what will be your, if this is given, this clue is given, right, what will be my output? I mean, so if you go n input, QE is 0.5, that means in my output, right, I have to calculate SNR out, right. What is that going to be? That is going to be square root of the number of photons, the random number of photons. How much is the number of photon, average number of photons? It's going to be 0.5 n, because the quantum efficiency is that. So, if one photon, right, you are going to get 50% out. So, the output you have 0.5 n, and the so we have given perfectly localize every photon. So, that means your SNR out is square root of 0.5 n. So, what is your DQE? DQE is nothing but your, apply your definition, right. DQE is this guy, SNR R out by SNR in square. When you substitute this, what is it that you are going to get? You are going to get 0.5. What does it say? Wow, we talked about dQe being less than equal to QE less than equal to 1. What did we find out? Oh, here is a case where your dQe and QE are same. Of course, they both are less than 1 because QE is less than 1. So, what does this say? Oh, this says in this case, right, in this hypothetical scenario, your dQe is equal to your QE, meaning there is no further, so that is this is the key. When we rule out the other possibilities, other variations, noise, then your dQe equal to QE. But typically that is not the case, right? Typically that need not be the case. This ideal perfect localization, other things may not happen. So there is going to be some fluctuation. So your dQe in general will be less than your QE. But in this hypothetical scenario, you can see that dQe equals your QE. Clear? So let's take another example. Here what do? I mean, first we took a hypothetical case. This is kind of little more closer, right, to reality than what we did now. Suppose an X-ray tube is set up to fire 10,000 photon bursts at a detector. So you have a detector, on the input side you have 10,000 photon bursts that is coming. The detector's output X is recorded as Xi. So the output is a random variable X and it's recorded as Xi. You have n photons, right? So now this measurement, right, X that you have measured, the output, that has a mean and variance like this. Oh, found to be X bar equal to 8,000 and your variance to be 40,000. Now the question is same thing. How do you calculate the signal to noise ratio? So dQe, right? So how do you get the dQe? So dQe we saw here also, right? You need SNR in, SNR out. So what is my input? Oh, my input is 10,000, right? So input side is relatively easy. Why? Because I have given that this random variable 10,000 photon bursts are on the input side. So we know what is the actual number of photons fired at X-ray tube follows a Poisson process. So the moment we recall this, we can quickly talk about mean and variance both equal to 10,000. Okay. So that means this is not a big deal, right? So I can get my SNR in is 10,000 divided by, this is variance is 10,000. So what do I need? Standard deviation. So it is square root of 10,000, right? So it's about 100. Wow, this is my input SNR. What is going to be my SNR output? Oh, you are given mean and variance, right? So you can write your output to be 8,000 divided by square root of this 40,000. What is that? That is going to be some 40. So what is your dQe? dQe is SNR out by SNR in by the whole square. So, in our case it is going to be 40 by 100 the whole square, which is 0.16. Clear? What does this say? What does this say? This says, oh, in the previous example we saw 0.5 as your QE, and your QE and DQE were same, whereas here your DQE is only 0.16, meaning only 16% of the photons are correctly identified, detected. So, right. So, that is what this tells. In other words, when we talk about the signal to noise ratio out by signal to noise ratio in, and how much it transforms the input signal to noise ratio, this kind of tells you that it is only about 60% detected correctly. That's one way of interpreting this. Clear? So, this is more straightforward to interpret. So, QE is fine, but it is a DQE that can be used to select the detector performance efficiency, right. Okay. So much for signal to noise ratio. What we need to do quickly is, signal to noise ratio is fine, we need to talk about Compton scattering, right. Compton scattering, what is Compton scattering? Oh, again, for what we did so far, the randomness came from, the noise came from the physics of the number of photons that are distributed, right, the time arrival difference. Whereas always there is going to be Compton scattering which due to the physics, right. So, what did the Compton scattering do? Compton scattering essentially sent out some photons with reduced energy, and it could come at angle. Okay, so that was Compton scattering. So, you have a signal that came from photoelectric effect, number of photons due to your photoelectric effect, but on top of it you also get some other photon from a different location, which is a Compton scattered. So, what it does is it reduces the image contrast and also reduces the signal to noise ratio. How does it reduce the image contrast? I hope you did this exercise when we did the introduction, right, for your image quality. I talked about how I think I did this experiment of taking my phone and switching on the torch and saying whether can you if I add, there is a contrast between my, if I remember right, that is the example we did, right, contrast between my shirt and skin. If I put a white light both on skin and my shirt, did the contrast go up or go down? I had actually asked you to try it at home and get a feel for it. We will do that mathematically now. So, produces unwanted effect where the image contrast is reduced. We will see why it is reduced, and it also decreases the signal to noise ratio. So, we will see these unwanted effects. We will write out these unwanted effect. So, in order to do that, first we will talk about the effect on contrast to noise ratio. Okay. So, what is our contrast? IT minus IB by IB. So, now we need to talk about Compton scattered, effect of Compton scattered. What does this Compton scattering do? Compton scattering essentially added, right, both I scattering, it added it to the target, it also added it to background. So, every pixel, remember, every pixel now gets additional intensity because of the scattering. Remember, I hope you now recall what we did, or at least what I asked you to do. So, C dashed is IT plus IS minus IB plus IS by IB plus IS. That is, I have added the scattered intensity to all the pixels, both in the target and the background. So, if you do that, what is the new contrast? So, you can manipulate this, you can get new contrast in terms of old contrast by a factor. So, more conveniently we can write this as C dash is equal to C by 1 plus IS by IB. So, if there is no scattering, then no problem, your contrast is not reduced. If you have scattering, right, if you have scattering, so there is this 1 plus some value, right. So, this is denominator that is greater than 1. So, your original contrast will be reduced, C dash will be less than C because of scattering. That is what we mean by decreases the image contrast. Okay. So, C dash is equal, so this IS by IB is given a term called as scatter to primary ratio. Okay. So, if I have more scatter to primary ratio, that means my contrast is going to reduce in this form because it is inversely related. So, if I have scatter to primary ratio increases, my denominator increases, and therefore my C dashed becomes less than my C. So, C is without scattering, C dashed is contrast with scattering. Clearly, if you have scattering, contrast in an image reduces, right. So, likewise what happens to our signal to noise ratio? Of course, we talked about signal to noise ratio also going down, but what we will do is show it, right. How do we show? Same thing, SNR with scatter is IT minus IB by sigma B, the same definition we started for SNR, right. Your target minus background intensity is divided by the variance. So, this is my signal. So, quickly we can write this. What do we need? We need to introduce scatter. So, if you introduce the scatter, so we can start to write SNR in terms of local contrast. Remember this, we did a few slides back. So, C IB by sigma B, but my new signal to noise ratio after my Compton scattering in effects are included will be C sigma B, right. So, you have your NB by NB plus NS. So, you have your new signal to noise ratio in terms of local contrast, right, NB by square root of NB plus NS. Of course, this is not in a convenient form, this is capturing, but it is not in a convenient form. What do I mean by convenient form? I need it in terms of some ratio, so we can quickly look at the relationship between SNR dashed and SNR, right. We kind of said that the Compton scattering reduces the SNR. So, this is a new SNR with Compton scattering included. So, we need to see this SNR dashed in terms of SNR, right. So, NS is the number of scattered photons per burst area A on the detector. Okay. So, this is the number of Compton scattered photons. So, your SNR dashed is this guy. I just manipulated, right. So, divided by square root of NB, numerator and denominator, and then you can take this guy in. Okay. So, why is this convenient form? Well, I have SNR dash C, I have something as NS by NB. Okay. So, SNR dashed is in terms of SNR by 1 plus IS by IB. So, I can just manipulate. So, the idea was I want to write my SNR dash in terms of SNR. SNR dash is equal to SNR times 1 by 1 plus IS by SB. What is this IS by IB? Oh, we already talked about scatter to primer ratio, right. So, SNR dashed is essentially, you can look at it from here, SNR, what would be without Compton scattering, due to your Compton scattering 1 by 1 plus. So, this guy goes greater than, right, the denominator 1 plus. So, this guy goes greater than 1, and so 1 by square root of this guy which is greater than 1. So, some factor less than 1. So, your SNR into a factor less than 1 is going to give your SNR dash. That means SNR dash is reduced. Okay. So, so this is a important aspect, right? Contrast, we are not going to talk about resolution. We talked about signal to noise ratio, we talked about Compton scattering included as well. So, we will just do one example here. Suppose 20% of incident X-ray photons have scattered in a certain material, right, before they arrive at the detector. What is the scatter to primary ratio? So, this is, you have your IS by IB. What is that? Because once you get that, by what factor is SNR degraded, right? So, this is straightforward, right? You can calculate this. What is given? What is given? So, what you are, once you get this is not a big issue. What is given? Oh, you are given 20% of the incident X-ray photon have been scattered. So, what is my, right, what do I need? I need IS by IB, IS by IB. So, what is IS, what is IB, right? I can give IB is about 90% of the, sorry, 80% of the N. This is proportional, right? Because you are given 20% is scattered. So, your IS is going to be proportional. Intensity, number of photons, they are proportional, right? So, IS is going to be 0.2 times the number of photons you are dealing with. Clear? So, once I have these, I can get my IS by IB. What is that? 0.2 by 0.8, okay, by 0.8, which is about 1 by 4, right. So, I have scatter to primary ratio. What is asked? By what factor SNR degraded? So, look at the, so SNR dashed by SNR, right. So, you have to calculate this guy, for which you have your IS by IB computed already, right. So, you are going to have loss, oh, okay. So, you are going to have 1 minus, right, 1 square root of 1 plus this point 1 by 4, right, IS by IB. So, this turns out to be about 11%, okay. So, how much is the, by what factor is this degraded? So, if this is 11% loss, so it is reducing the SNR by 11% because of Compton scattering, okay. So, this is a very important aspect, because image quality, now what we did is, we are able to see most of it is related to the number of photons and the inherent contrast, right. And then we talked about detector efficiency. So, even after you have a particular detector, if you can manipulate N, you can manipulate your signal to noise ratio. So, whichever form we saw, with scattering, without scattering, noise by itself, this N, number of photons, plays a important part. Okay. So much for noise and scattering, which is to do with your image quality. So, now we will just summarize what we have covered so far in this projection radiography. In projection radiography, we talked about the system, right, consisting of your X-ray tube and then all the other parts, filtration, field of view restriction, compensation filters, grids, right, including film detector, in fact the intensifying screen, we talked about all that. And then we talked about, after it hits the detector, that input X-ray exposure converted to light photon, how does that expose the film, and then the development of the film, and what you talked about, right. So, detector reading is proportional to the number of unabsorbed X-ray photons, right, which depends on the overall attenuation path of the source. So, in some sense here you have to think about why the in a typical X-ray bone comes out to be white, right. If you have a fracture, the fracture is coming out to be dark. Why is bone white? Because there is more attenuation. So, the film is not exposed, is exposed by less number of photons, because the bones absorb the X-ray photons. So, if a detector is behind the path that has bone, that would receive less number of X-ray photons, and therefore less darkening of your X-ray film. Okay. So, degree of this darkening is related by the S curve or the H and D curve that we talked about, and then finally we talked about the noise, both due to detector noise and the inherent physics, which is your Compton scattering. Okay. So, that concludes the aspects that we wanted to cover with respect to projection radiography. So, from subsequent lectures we will talk about the next modality, which is going to be your X-ray CT. Thank you.